Okay, so we are looking at projectile motion 2, part 2. Here's question number 3. On a long level play field, a player kicks a football from an initial speed of 40 meters per second. And there's our first given. That's our initial velocity at an angle of 30 degrees from the ground. So we know theta also, and that is going to be 30 degrees. At what time does the ball reach its highest point? So our unknown is going to be time. All right. So let's turn this into, let's do a quick little drawing here. We've got a ball launched at 30 meters per second at an angle of 30 degrees from the ground. All right, so we need to know what the velocity is in the horizontal direction. So our vertical direction. So our initial velocity in the vertical direction here. Since that's opposite the side of the angle, we want to make sure to use the sine function. So we need to do the initial velocity of the ball is equal to, in the vertical direction, is equal to the initial velocity times the sine of the angle here, 30 degrees. So that initial velocity in the vertical direction equal to the initial velocity, which is 40 meters per second, times the sine of 30 degrees. All right, so if we look at the sine of 30 degrees over here, the sine of 30 degrees is 1/2. So, oops, sorry about that. We've got my pen kind of messing up here still a little bit. Do this. See if this will fix it. All right, so we've got 40 times 1/2. So the initial vertical velocity should be 20 meters per second. So an equation we want to use, if we go to your formula chart, if we know that the change in velocity over change in time is acceleration, then we can rearrange this to solve for time and say time is equal to our change in velocity over the acceleration. So our change in velocity is 20 meters per second. And then the acceleration will be 10 meters per second squared, and that gives us a time of 2 seconds. So we know that's going to take 2 seconds for the ball to go from here to its highest point up here, if it were thrown straight up in the air. Or it could be, so if it were thrown straight up in the air like that, or it could even be launched at that angle of 30 degrees, come back down. It's still going to take the same amount of time to come up to the very top, which is 2 seconds. So it takes 2 seconds to get up to the top of its projection. All right, now let's look at the next part of this. B, what is the greatest height reached by the ball during projectile motion? Now, for this next part, we need to look at that height. And when we were thinking about it, this thing being launched, coming up here, coming back down, okay? When we're doing that, we know that the time to go up and the time to come down are identical. The distances that it goes are the same. So I prefer actually to start here at the top and then come down here to the bottom. Okay, so those are the 2 places I'm going to choose to do my calculations from. All right, so we know again that it takes 2 seconds to get up here to the top. And we also know that the vertical velocity, which we looked at already, 20 meters per second. Okay, so if we look at that vertical velocity, it's going to be 20 meters per second. Now we could consider it a negative or whatever at this point, but we know it's going to be 20 meters per second in the downward direction at that point. So let's see. we need to figure out height too. How far, what is that? Y. So our givens, again, we know time now is 2 seconds. We know basically a final velocity is 20 meters per second vertically, so this final velocity. The initial velocity vertically, as it starts up here, when it's falling, there is no velocity vertically. There's only horizontal velocity at this point, so the vertical velocity is 0 at that point. So now we want to solve for our unknown. How high does this thing go? Okay, or how far does it fall either way? Well, let's look at an equation for this. Let's do y equals 1/2 a t squared plus v naught t plus y naught. So let's say that this is 0 because the initial velocity, there's no initial velocity vertically at this point. So this is 0. Anything multiplied by 0 is 0. And let's consider that our start. So that's 0. So up here, this is our start. So let's figure out how far this thing falls in this equation right here by plugging in some numbers. So we know this is 10, and we know it takes 2 seconds. So let's say that it is half of 10 is 5. And I forgot my square right there. 2 squared is 4. So 5 times 4 is 20 meters. So we know this falls a vertical distance of 20 meters. So the greatest height reached by the ball is 20 meters. It also falls 20 meters. So your change in vertical distance from the ground at this point would be 20 meters. All right, now let's look at number 4. It says an artillery shell is fired with an initial velocity of 400 meters per second at an angle of 53 degrees. So 400 meters per second at an angle of 53 degrees. So let's write down some of that information. I'm going to write down my givens. Angle 53 degrees. Okay. And we want to know how much time passes before this shell strikes the ground. So when we launch this thing, so we're going to launch this at a fairly good angle and say we launch it at 400 meters per second. There's our initial velocity. And we launch that at 53 degrees. All right, we want to know time. Well, again, we need to know vertical for time, vertical velocity, so the initial vertical velocity. Coming back to that, going back to our equation for that, we remember that it should be v naught times the sine of the angle, so let's plug in our numbers. 400 times the sine of 53 degrees. Well, what is the sine of 53 degrees? Let's go take a look at that. Sine of 53 degrees, well, that's given to us right over here, and the sine of 53 degrees is 4/5. So we can come back and look at that here. So 400 times 4/5, which would be 1600 divided by 5, which gives us 320 meters per second. So if this thing is thrown straight upwards at 320 meters per second, how long does it take to go up and come back down? Well, since it's going up and coming back down, we know that we're going to have to do 2 times that initial velocity, just like what we did earlier in part 1, divided by the acceleration to get time. And that just comes from the equation for time being change in velocity over acceleration, where change in velocity would be 2 times that initial velocity, because as it's launched going up, it's going 320 meters per second, and it goes up, it comes back down, and when it comes back down, it's still going 320 meters per second, but now in the opposite direction. So our change would be 2 times that initial velocity. So let's do that. 2 times 320 divided by 10, which gives us 640 divided by 10, which is 64 seconds. So there's our answer. Now, let's go look at B. What horizontal distance does the shell travel before striking the ground? Right, so now we've got to look at that same shell being fired at 400 meters per second. But this time, instead of caring about the vertical velocity, now we need to know the initial horizontal velocity. And remember, once that gets launched, that horizontal velocity remains constant. So we use the sine function for the other one. For this one, for the horizontal, we're going to end up using the cosine function. So we need to know the initial velocity times the cosine of the angle here. So let's plug in numbers, the initial velocity being 400 and the cosine of 53 degrees. So let's go take a look at the cosine of 53 degrees. Cosine 53 degrees 3/5 right here. Okay. So 400 times 3/5. Times 3/5. All right. So 400 times 3 would be 1200, and 1200 divided by 5 gives us 240 meters per second horizontally. So we know this is going at 240 meters per second horizontally. And so as this thing travels up through the air, comes back down, doesn't matter where it's at, that horizontal velocity is always going to be 240 meters per second as it is traveling. That stays constant as long as that's the horizontal velocity, 240 meters per second. So how long is it traveling at that? Well, we just figured out the time in the previous one, 64 seconds. So we want to know for distance, it would be the velocity multiplied by time. So our velocity is 240 meters per second horizontally times 64 seconds. Okay, and so that would give us 15,360 meters there. Now we could also round that with significant digits, but we'll just keep it like that for now. So let's look at question number 5 in the third part to this.